thinking for sure we'd be started on time this time, but no, I got hijacked by those two. Okay, so let's go on from here. Let me go through just a couple of announcements. I don't usually see or hear from y'all on Fridays, but just in case you're looking for me on Friday, most Fridays I'm on the Birmingham West Campus right across there in the B building from 8 to 12. Usually there before 8 and almost always there after 12. Not this Friday. Day after tomorrow, I've got to drive down to Mobile for a 3-hour meeting, 3.5-hour meeting now. I have to leave about 7 in the morning to be there by 11:30. And hopefully I can make it in that time. And then we meet until 3, and then I drive back and hopefully we'll get back by probably around 8 or so. But I've got to first go to the Bessemer campus and leave off the vehicle and then take my vehicle home. So it'll probably be even later than 8 before I get there. So it's going to be a long day, but I won't be on either campus at all this Friday. Now, next Friday, I also have a eye doctor's appointment at 8:15 Friday morning, but it's out in Bessemer. It's at the UAB West right across from the campus there. So I'm going to go there first thing in the morning, go to my appointment, and then probably go to the Birmingham campus after that. I just don't know what time that'll be. I'm guessing I'll be over here around 10, maybe before. It could be later. One other thing, midterm was last night at midnight. That was it. Okay, we're now in the second half of the term. And they do periodically, usually shortly after midterm, ask for midterm progress reports. And for all of you here, you're in good shape. It's 2 people haven't turned in even the first test, and 1 other person didn't do well on the first test. So anyway, those will, if I don't get anything by the time they ask for it, then those will probably have reports going out. Not that it really matters that much, but you might start getting things like contacted by people. Do you need tutoring? Do you need counseling? You know, that kind of stuff. Just to avoid the hassle, it's a good idea to get in your materials. Okay. Now, any questions before we get going today? Sorry we're late getting started. All right, we're on page 331, if my memory's right. Chapter 12 is matter, and I don't remember which section this is. It's section 12.5, density. Quite a few examples in here, so let's hit another one. Find the mass density of a ball bearing with a mass of 22.0 grams. So the mass is 22.0 grams. Okay? And a radius, now this is a ball bearing. My little diagrams are not very good. A sphere, this is on page 331, number 2. The radius of this ball bearing, that doesn't look like a very good sphere, but the radius is 0.875 centimeters. R is equal to 0.875 centimeters. Okay. And it's asking for mass density. Now, the mass density here is given in the table in kilograms per cubic meter. So we got 2 conversions to make. Now you can either continue through the problem doing it this way and then maybe at the back of the book find the conversion in the conversion table, or you can change things right here. Probably not a bad idea to go on and change them here. So let's convert this mass from 22.0 grams. We need to convert that to kilograms. So that's going to become a bigger unit, so you're going to need a smaller number. Do you know how to make that conversion right off the top?
You have to divide, right?
Yeah?
By 1,000.
By 1,000, exactly. So you can divide, you can do that very thing you said, divide by 1,000, and it's 1,000 grams per kilogram. and the grams will go out, the kilograms moves up top. So dividing by 1,000 is like moving a decimal 3 places to the left. So this will be 0.022 kilograms. 220 kilograms. Okay. So we got the mass converted. Okay. So this is now the mass in kilograms. We got to get the centimeters converted to meters. Does anyone know how to do that one?
Is that 10,000?
No, it's meters.
Hold on.
Yeah. Okay.
Centi is cent. So it's
No, centi is 100. Think of a cent. It's a hundredth of a penny. Okay? And you're going to minute. Oh, you were right before. Okay? 10,000, you're absolutely right. Because you're going from the small unit, a hundredth, to, yeah. Okay, think of it this way. Okay? That is a centimeter, approximately, across my little fingernail. Okay? This is about a meter from this ear to there. And it would take 100 of those. 100 centimeters in a meter. Okay? So, you're going from a smaller unit to a bigger unit, so you're going to have to go to a smaller number. So it's 2 more decimal places to the left. So this will be 0.00875. No, that's not enough. Yeah, it is. Yeah, that's right. Because that's the same as 8.75 millimeters, and that would be. So this is how many meters. Now that's the radius. Before we can go, we need the volume of that sphere. That's just the radius of the sphere. Does anyone know the volume of a sphere? Now, most of these books... What's that?
I think that's square.
Okay. No, okay. This is a formula you'll need to go from radius to volume. Let me see if I've got it. Formulas from physics. No. Not in the front. Okay. Okay. Let's see if it's in the back. Yes, here we go. Back inside cover of your text. Okay, not the hard cover, but the inside of that. There's a sphere at the bottom, and it has 2 formulas for volumes, one for area. The one with radius is volume is equal to 4/3 pi r cubed. Okay, so your volume is 4/3 pi r cubed. So that would be 4 divided by 3 times pi, and most of your calculators have a pi key, right? And then you'll have the radius cubed, and that's 0.00875 meters cubed. Now that's going to be an incredibly small number. So stand by to expect that to be small. Okay. Hey. Look in place here. And this is
Mason.
Mason, got it. Jasmine Mason. Just had to find you. Okay. Yeah, there's a key in there for pi, I'm pretty sure. We're on page 331, example 2, middle of the page. And you got to cube that number. And that's the one you do a caret 3 probably, unless you have a cubing key.
Oh.
Really small number.
I hope this is right.
No, it's just the volume. Well, okay, now they're doing it differently, so don't follow theirs too much. Okay, so a very, very small number. It should have a 2, 8, and a 1 in it. Does it? It does not. Well, then there may be something wrong with it. All right. Let me...
Maybe I didn't do the cube part right. Let me see. So I got the 4. Was I supposed to put it in like that? Or divide the 4 by the 3 first?
That's how I do it, but I don't know what your thing there is. That probably 4/3 pi, and then what, 0, 0, 8, 7, 5, and let's see how you cube it. Wait, okay. No, you did a square root. Okay. 8, 7, 5. And,
Here.
yeah.
And then, which one did you use?
Use this one right here.
Wait, you supposed to use second or just
this
mention?
one right here, that, and then do a 3.
Oh, okay.
Yeah, 8, 2, 1. Yeah.
Okay.
Right.
So,
Like I said, a very, very, very small number. You ready to get it? Huh? Not, okay, yeah.
just a very
That's so far so good.
this far.
Minus 6, yeah. Very good. All right, anyone else have a problem with it? Okay. Now, you've got that number, and what you've got to do, what is density? This is all to set up to do the density. What is mass density? And that symbol they use is D sub M. What is that formula? Mass per unit volume, not velocity, volume. Mass per unit volume. And the mass was the 0.0, that's ugly. Let me see if I can clean that up a little bit. Okay. 0.0220 kilograms divided by that number you had, which was I think on yours was a 2.806, or you had a bunch of decimals numbers, 806, blah, 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 times 10 to the minus 6 yours was? Is that right? I'm just going by yours. That was one way. You just put in that number, but be sure you get the right number of zeros in there. Okay. Some of the calculators have a store key, and when you have a big number like that, just store it and then do the 0.220 divided by recall, and then do that. And this would be in cubic meters. And when you do that, you should get a fairly dense thing. I'm going to guess on the order of 7,000, 8,000, something along in there. I'm just guessing.
okay, then you do that times 10 to the 6.
Minus 6. But that's, I put hers in there. I don't know.
Oh, so, okay, so I just do minus times 10.
No, okay. If you move the decimal over however many places you do it, that would be 10 to the minus 6.
Never mind.
Yeah.
I get what you're
If you did your number, you use your number just like you had it. Whichever way you do it. Anyone get an answer yet?
saying. 7,
Yep.
8, 4, 0.
They got 7830. I don't know, maybe round off. 830 is what the book got. And that would be kilograms per cubic meter. Ops. Goodness gracious, this thing is driving me nuts. Okay. Per cubic meter. Now, they may have had the round off error because they did round off much sooner than we did. Okay? They kept the 220, that's okay. But when they did 2.81, I did 2.806 something, and it may have another round, but I bet you ours is more correct than this. I bet you the 7840 is probably better because you kept better digits. Okay. Does everybody see how you get that? Now, just to do the problem, you had to get the right units. Okay. They gave it in grams. They want it in kilograms. So you had to make that conversion. They gave you centimeters for the radius. They want it in meters. So we did that conversion. And then they did the formula for the volume. We did that. And then we did the division. Was there a question? Oh, okay. I thought it looked like you had some. Everybody got it? All right. So that was example 2. Ready to move to example 3? Yay or nay? Okay. Find the weight density of a gallon of water. So you got 1 gallon of water. Okay. Weighing 8.34 pounds. So what do they call that? F sub W for weight, 8.34 pounds. All right. Now, they give the volume as a gallon, which really is a capacity, and in the weight density we use pound per cubic feet, so we need to know how many cubic feet are in a gallon. And that's where we go back to the tables in the back of the book. Okay. So back in the back of the book, around page 688 or so, let's see if we can find it. They actually start with 686. Length, area, volume. There's a volume table on page 687. And you notice they have, oh, there it goes. 1 U.S. fluid gallon is, there they have it, 0.134 cubic feet. Do you see that in the table? Back of the book, page 687, the top table, table 4. After the conversions they have at the very top of the table, on next to the last line they say 1 U.S. fluid gallon equals 4 U.S. fluid quarts, 8 U.S. fluid pints, 128 U.S. fluid ounces, or, and then they give cubic inches and then cubic feet, 0.134 cubic feet. Okay? Now I had a marker in place and I've lost, oh, there it is. Okay. So 0.134, is that what I said? Okay. So this is equal to 0.134 cubic feet. Okay? And that's what a gallon is. Well, this is the volume of 1 gallon of water. Okay? So F sub W, density, and this is a weight density, which they call D sub W. What is its formula? Weight, F sub W, divided by volume. Okay? And that was 8.34. Not many conversions to make here, just that one, and it was a simple one. 8.34 pounds divided by 0.134 cubic feet, because that happens to be the number of cubic feet in 1 gallon, and you see what you get. Should be 70 or 80, probably in the 70s, maybe even 60s.
62.
Yeah. 62 point what? 23. Okay, and since we only have 3 significant digits, we'll round that to 62.2 pounds per cubic foot. Okay? If you look in the table across the page, you'll see it says 62.4 is normal. So yeah, that's pretty close to what you would expect. This may have been water at a slightly higher temperature or something like that. No, they get. Okay. All right. They do a different conversion. They do first from cubic inches. Wait a minute. What are they doing here? They take the gallon, which is 231 cubic inches. We use the 1.134 cubic feet. So that, just the difference in what we're using for a conversion, that accounts for it. It's not far off. That's just as good, just as close. Okay. If you're within that kind of ballpark. Now, if you had 6.22, okay, that's way off. Or 622, that would be way off. 62.2 versus 62.4, that's close enough. Just depends on which conversion you're using. Okay? Good for 3. Let's move on to 4. Find the weight density of a can of oil, that's 1 quart, weighing 1.190 pounds. So we want the weight density of 1 quart of oil. Okay, weighing 1.9, F sub W is 1.90 pounds. Okay, so now we got to convert a quart to cubic feet. Well, a quart is 1/4 of a gallon, right? And what did we use before? 0.134 cubic feet. Divide that by 4, whatever that is. You can do that if you want to. That would be 0.035 or something like that.
Yeah,
3075. Okay, we'll keep all those digits for now. That's cubic feet per quart. Okay, now what we'll do, and that's what we have, is 1 quart. So our weight density, which is D sub W, that is the weight, 1.90 pounds, divided by 0.03075 cubic feet per quart. So that would be pounds per cubic feet. What does that give us? Looks like to me about 60, a little bit less than 60. 61.
7, 8.
Okay. Let's just round that because we have 3 significant digits. Everything that was given to us, we'll do it 61.8 pounds per cubic foot. See what they got in the book? Whoa! Whoa!
That's way off.
Yeah, that's pretty far off. I thought it would be. Any trouble finding it? All right, good deal. Okay, thank you. Okay, let's check our numbers here. 0.134 divided by 4. Now, did I remember it? 1.134, is that right? 0.134, yeah, that's cubic feet per gallon. Divide that by 4, and that would be 0.03. I think it's bigger than 0.075, isn't it? 0.134 divided by 4. Because 0.12 divided by 4 is... Maybe not, though. Let me think. Yeah, that's where we made our error, I think. What's that?
0.134 divided by 4 is supposed to be 0.0335.
335?
Yes,
Okay.
that's what it is.
Okay. 335. Okay. And then we'll plug that in down here. And that will change this and that. Okay, I mean 3, 5. And that would be 56. What?
7.1.
7.1. So we'll round that to 56.7 pounds per cubic feet. Let's see what they got. 56.9. So
the number's so far from the book, though?
It's not that far. I mean, that's only 0.2 out of 50 some. That's pretty close. The reason is they're using the cubic inches and making a conversion there, where we're using cubic feet and not having to convert. I don't know who's more accurate. I think they're probably both pretty close to the same, but they're not to 3 digits, but they're close, awfully close. Okay? Now, all right with that one, move on to the next. Okay, this one. A quantity of gasoline weighs 5.50 pounds. Oh, and by the way, I wanted to compare the other to the table that we had. Oil was about 54.2. They got 56.9. We got 56.7. See, we were actually closer to what the table said. But, of course, you know, different oils have different densities. So this is 5.50 pounds with a weight density of, so this is the mass, now this is the weight, F sub W is equal to that. The weight density, which is D sub W, is equal to 42.0 pounds per cubic feet. Okay? The question is find the volume. So now we're looking for volume. How are we going to do that? Okay? You don't need to look in the back, I don't think. What is our density formula? Do you know it? We've been using it. Yeah, weight divided by volume. So to get volume, now you could set up your circle or your triangle if you like those, or you could just do the math. Which would you rather do? Anybody? Do the math? Well, you're looking for the volume, so I don't like it being in a denominator. So I'm going to multiply both sides by volume, right? That gets it out of the denominator into the numerator where we like it to be. But now the density's in the way, so let's divide by the weight density. And then they will go out, and your volume would equal the weight, forced you to weight, divided by the weight density. And we know the force is 5.50 pounds, which is not very heavy, divided by 42.0 pounds per cubic foot. So it's going to be a pretty small number, but it's a pretty big unit. A cubic foot is a pretty good size, you know. Notice here the pounds will cancel out, and you're left with 1 over cubic feet, which when you flip it up, it becomes cubic feet. Units are your friends. Be nice to them. Care for them. Nurture them.
So okay.
Is this in the way?
No.
Oh, it's not. Okay. They left it here, and that TV was right in the way, so I had to move it out of the way. 0.130, and that would be cubic feet. Let's see what they got. They got 0.131 cubic feet.
Well, they must be, you know what, it is a 9 behind this, alright?
Oh, is there? Okay.
See, it's extra numbers behind those. So
right.
Yeah.
That's why usually you give me 4, so I round. You only gave me 3 this time, so I thought you were rounding. Okay.
It's a lot, yeah. I'm like, where do you stop it?
Well, no, you just go one past the number you got.
Okay.
We got 3 significant digits,
Okay.
go to the 4th, and then that determines what your
Okay,
third
so
one
that
is.
makes clear sense now. with
Yeah.
the other ones, so,
Just
yeah,
take it one more than what your others are, and then round down or up, whichever it takes. All right, 0.131 cubic feet. All right. All right. Now, what if you have something that doesn't have a very well-defined volume, like a rock, okay? The density of an irregular solid, like a rock or anything else, let's see, not that you would want to do this, but your calculator there. It has buttons that stack up and things like that. If that were a solid, not something with holes in it, which you wouldn't want to do this for. I'm trying to think of something else. On a bigger scale, that cart back there. It's hard to determine the volume of that cart, but what you could do, if you had a big enough tank full of water and you had a drain just at the right place, you had the water absolutely full, drop that into it, or lower it carefully into it, measure the amount of water that comes out, that's the volume of water, would be the volume of that thing. Same thing of a rock, okay? You can find the amount of water the solid displaces, which is the same as the volume of the irregular solid. The volume of water in the small beaker equals the volume of the rock, if you're looking at the picture. Now, this picture is not on the slide set, I don't think. I checked before, and the last slide in the slide set was the, we'll just check and see. Was that one. You see, there aren't any further down there. Oh, wait. No, that wasn't it. So you see they don't have any more slides on here, so I can't show you the book, but if you got the book, you can see it. Come on. Okay. Go back to black. Okay. Now, example 6 then has a rock that's easy to determine the mass. You just put it on a scale. Okay. A rock with a mass of 10.8 kilograms. So the mass of the rock is 10.8 kilograms. Okay. Displaces 3,200 cubic centimeters of water. So this is the volume of the water is 3,200 cubic centimeters. Now another name for cubic centimeters is milliliter. Exactly the same thing. That's a capacity, this is a volume. But we really don't want it in cubic centimeters. We want it in cubic meters. So we're going to have to make a conversion here to cubic meters, because the table over there always gave the volumes in kilogram per cubic meter. So we're going to have to multiply blank blank equal blank, and we want this in cubic meters. Okay? So what unit is going to go where? Always put the units in their place. Don't worry about the numbers yet. Put the units in their place. What unit will go where? One goes above the line, one goes below the line. Cubic meters go in one place, cubic centimeters in the other. Or right now, let's just do meters and centimeters. One goes above, one goes below. Which goes where? Centimeters at the bottom and meters at the top. Now, how many meters in a centimeter are centimeters in a meter? Now we do the numbers. How many centimeters in a meter or how many meters in a centimeter? You decide which one you're going to do. How many cents in a dollar? 100. 100 centimeters, centimeters, like I said, a dollar, okay, in 1 meter. But we don't have meters and centimeters. We have cubic. So we're going to have to cube this, cube that, and cube that. Okay, I can cube 1, I can cube m, I can cube cm, but to cube 100, that takes it and triples the number of zeros. So it'd be 1, 0, 0, 0, 0, 0, 0. That's 1 million cubic centimeters is 1 cubic meter. So that's what we've got to divide by. But dividing by that is basically moving your decimal 6 places to the left. Well, there's 4 places, and just 2 more gets us there. So that's 0.00320. That's how many cubic meters. Now, what is your density? Mass density? D sub m. It's what? No, that's weight density. Mass density is mass per unit volume. Okay? And your mass was 10.8. They gave it to us in kilograms. That's exactly what we want, kilograms, divided by 0.00320 cubic meters. Okay, when you do this, give me at least 4 digits.
Okay.
Because this is 3 and that's 3. Second? I can't hear you. It's going to be a pretty big number. About 3,000, huh? Yeah, okay, what do you get? 3,375? Okay. Count 3 digits, look to the right, it's a 5, bump it up by 1. 3,380 kilograms per cubic meter. Okay. Now, let's see, what was this that we're talking about? A rock. Let's see, they probably don't have a rock in the table, but it probably wouldn't be too far from what aluminum is. Aluminum's 2,700. Between aluminum and iron, because we don't have silicon. So yeah, that sounds reasonable. It's in the right ballpark. Let's see what they got. 3,380. Good for them. Kilograms per cubic meter. My writing stinks, but other than that. Okay. Per cubic meter. All right. And that's how you do densities of irregular shaped objects. You fill a container completely full of water, especially if you have one with a spout like this, till just after the water has started spilling over. Get it right up to that point. Dump out that water that spilled over. Then very slowly and carefully lower the volume that you're interested in into that. Make sure it goes completely underneath the water. And when it does, the amount of water you caught out the spout, that gives you the volume of the material. Okay. Here's another one similar to it. All right, to erase. A rock displaces 3 gallons of water. So this is your capacity or volume, 3.00 gallons of water. This sounds like a U.S. customary one to me, and has a weight density. So the D sub W for this rock, somehow you knew, was 156 pounds per cubic feet. 156 pounds per cubic foot. I don't know those units all that well, but that sounds reasonable. Okay? What is the weight? So we're looking this time for F sub W, which is the weight. How are we going to get that? First, you look at your units. They are not compatible. This is gallons. We want it in cubic feet. So let's first do that. Now, you remember that conversion? 0.134? 0.134. And that's how many cubic feet in 1 gallon. All right, so the gallons cancel out. That gives you cubic feet. So this volume is 3 times that. That would be yeah, 0.402 maybe. I'm doing it in my head.
So we're doing the
3 times 0.134.
Okay, 0.402.
Okay, 0.402. And that would be cubic feet. All right. Now, how do we get our weight from that?
And then you do the 156.
Okay.
Divided by the 0.4.
Okay. Is that going to give it to you? Let's go back to our original okay. The units say no, okay? And pay attention to the units. They're your friends, okay? Or you could go back to your density formula. What was that? Density, weight density is equal to weight, which is force due to weight, divided by volume. This time we're trying to solve for force, not volume. So how do we do that? You do what? Yeah, you're trying to isolate the force. How do you get rid of that volume? Same way we did it last time. Multiply by volume, but you do it to both sides. This is, and that gives you the force. This is equal to mass density, no, weight density, d sub w times the volume, which in this case is 156 pounds per cubic foot. Multiply that by 0.402 cubic feet. Okay? And notice, this is why I say units are your friends. The cubic feet cancel out. That gives you pounds. That's exactly what we measure weight in. Okay? It's in pounds. And this will be something greater than 60. 62.7? 62.7, and that would be pounds. Okay? Let's see. This was a rock. Oh yeah, 62.7 pounds. Let's see what they got in the book. 62.6. So they rounded a little bit differently than we did, but should be right close to the same. Yeah, you see, they went to the cubic inches things rather than using cubic feet. Why use cubic inches if you're wanting your answer in cubic feet? So, but they just used it this fine. All right. Good deal. Ready to go to example 8? Oh, new topic here. To compare densities of two materials, we compare each with the density of water. Water is the most common compound on the surface of the earth. It covers 60–70% of the earth's surface is covered by water. In some places that's miles deep. Water is water everywhere, okay? Especially the last year or so we've had rain like crazy, okay? So if we compare it to the specific density of water, now in 1 unit, that's a real handy thing. Like if you're in the SI units, no, not SI units, the metric units where you have 1 gram per cubic centimeter is the density of water, then everything is going to be compared to that, okay? So dividing by 1 is pretty easy to do. But you see, we're using kilograms per cubic meter, but when you divide by the density of water, which is 1,000 kilograms per cubic meter, you still come up with a pretty reasonable number. And when you're dividing the weight density by 62.4, you should come up with the same unit. This is called the specific gravity of water. Okay? Sort of a new concept. It's very similar to density, but specific gravity. Now, that's not a new kind of gravity. This is just what they call it. The specific gravity of any material is its density of the material divided by the density of water. And guess what? It doesn't matter which density you use. If you use the weight density of the material, use the weight density of water. You're going to get the same number if you use the mass density of water of the material, but then divided by the mass density of water. The specific gravity is unique to the individual. It doesn't matter what units you use. So this is a much cleaner thing. You don't have to haul around units, because guess what? The units, it has no units, because this is kilograms per cubic meter. That's kilograms per cubic meter. The units cancel out. If that was pounds per cubic feet divided by pounds per cubic feet, those cancel out. So you just get a pure number. It's a unitless quantity. So let's do example 8. Ready for it? Okay. The density of iron, this is the mass density of iron. How did I know that? 7,830 kilograms per cubic meter. How did I know we were talking about mass density? Kilograms measures mass. Pounds measures weight. So this is a mass density. It says find the specific gravity. Now they use SPGR. Pretty creative, okay? Doesn't have a symbol or anything, just SPGR. And what would that be? It would be the density of iron, and that's mass density, divided by what? Density of water. The mass density of water. Be sure you use mass density. Okay? So that would be 7,830, now notice how easy this is going to be, kilograms per cubic meter. Keep the units because they're your friends. Density of water, use the mass density of water from the previous table, and you know exactly what that is. I just called it out to you. 1,000 kilograms per cubic meter. It's going to be a pretty easy calculation, isn't it? Guess what? The units go out, and here you just move your decimal 3 places there, and you get 7.83 done. No units involved. Specific gravity has no units. We probably will see one. But it may not be in mass density. It may be in weight density. But you can still do it. 7.83. No units. And what does that mean? It means that iron is almost 8 times as dense as water. Okay? That's why iron sinks like a rock. Stronger than a rock. So let's do example 9. Ready? Yay? Say again? Yeah, this section has a lot. Example 9. The density of oil is 54. This is density of oil. I don't know which one yet. 54.2 pounds per cubic foot. Now do we know which one it is? What density is that? Weight density, because weight is in pounds. Mass is in kilograms. Find the specific gravity. So what will we need to know? The SPGR is what? The density of the material. This was oil, I believe it was. Divided by the density of what? water. Okay, but which density do we use of water? We better use the weight density of water. Turn back to that table, just 2 pages before. You see it's 62.4 pounds per cubic foot. That table right there.
Oh, okay.
See the liquids, water, last one. The weight density. Yeah. Okay, pull out your, and notice the units go out again. That's why you hang on to the units, because they tell you whether you got the right ones or not. Okay? And what do you get? 0. About 8 something maybe? 8685. So you'll probably round that up. Count 3 digits. 0.869. No units. Okay. Oops, I'm back on the wrong page. Yep, 0.869. That means oil is less dense than water, and that's why oil floats. And that's why when you have an oil spill, it all comes to the surface, and that's what chokes out the oxygen from getting to the plants and animals underneath, and that's why things die. Oil spills are bad things. All right, now, they mention here a device called a hydrometer. And hydro usually means water, so this is something that measures water. That's what it sounds like it is. It's actually a sealed glass tube weighted at one end so that it floats vertically in a liquid. It sinks in the liquid until it displaces the amount of liquid equal to its weight, and that would then tell you the specific gravity of that. That's how it's scaled. Now, you use this for a variety of things. The place I've seen it most is measuring to see if you have enough antifreeze in your cooling system. And they'll put a hydrometer there, and they know what your specific gravity needs to be. And if you don't have it, they'll say you need more antifreeze. Okay. It's used for other things as well. I bet you somewhere they probably use it for measuring specific gravity of blood. Of course, you have to have a pretty large quantity of blood, so it would be a pretty small hydrometer to use that. They probably do a different way from that. But anyway, also batteries, lead storage batteries. Fully charged specific gravity should be about 1.3, but when it's old and fairly well discharged, it gets down to 1.15. It's getting closer to pure water. Okay. Antifreeze water solutions, specific gravity goes down to about minus 1.24 degrees Celsius, which is maybe about 30 degrees Fahrenheit. But then at higher temperatures, at lower temperatures, very low temperatures, specific gravity goes up. And then they show specific gravities of common liquids. Benzene, a little bit less dense than water. Ethyl alcohol, quite a bit. Gasoline, even less dense. Kerosene, a bit more dense, but still lighter than water. Mercury, goodness gracious, look at mercury. 13.6. Very dense liquid, about the densest liquid you can find. Seawater, a little more dense than water. Sulfuric acid, 1.84. That was what was in your lead storage battery, but it's not pure. You mix it with water, so that's why you had a 1.30 before. Turpentine, it's a little less dense than water, and then water, of course, is 1.00. Okay. That finishes the chapter, or the section, which has problems at the end. It says express mass densities in kilograms per cubic meter, weight densities in pounds per cubic foot. Do any of the odds 1 through 7, any of the other odds, 9 through 23. You can do any of the odds 25 to 29, and then either 31 or 33, and then you could try 35 or 37 if you'd like. Okay? There's a glossary there if you want to review some terms. There's some review questions that are more conceptual in nature. They do have a formula page there, so there's your formulas right there that you might need. And then they have some review questions, which are pretty good for getting concepts down. But the review problems are going to be closer to what you see on your test. And again, the odd numbers have answers in the back. So any of the odds 1 through 7 perhaps, any of the odds 9 through 19. All right. That pretty much wraps up Chapter 12. They have an applied concepts there. You can look at those. You certainly can study those. All right. We're not doing Chapter 13 or 14. Let me get out of this to get to I want to move some things around, so I'm going to move this and move this. All right, we just finished 12. We now move to 16. All right, Chapter 16. We're skipping fluids. Skipping fluids, that's 13. 14, temperature and heat transfer. Good stuff, but we don't have time for it nor a need for it. 15, properties of gases. We've already done some things with that, but that is more, but we're skipping that too. And now we're in 16, which is wave motions and sound. And what are y'all studying for? Sonography, sound, okay? So wave motion and sound, this is one of the more important chapters that we'll be doing. All right, so let's get started from this slideshow. Excuse me, I got hiccups. All right. Good deal. Let's talk a little bit about what a wave is. Now, when you think of a wave, what do you think of? Second?
The ocean.
Yeah, the ocean, the waves coming in. And that's really a pretty good way to think of a wave. If you think of that wave, it has a crest when you've got the most of the water there, and it has a trough where the water is the lowest or the least. Well, when I'm talking to you, the act of talking, if you hold your hand in front of your mouth when you're speaking, you feel little pulses of air. That's exactly how I'm communicating to you. I'm creating waves, troughs, peaks and troughs. Okay? And guess what? That's what hits your eardrum. And your eardrums are so wonderful, they can sense those tiny little vibrations, and they vibrate with that. And then you got all these amplifiers inside your ear, the stamen and the pistil, and I don't know what all things there are back there that you have, and they amplify that, and the neural system takes it to the brain, and that's how you hear. Just amazing.
I don't know how they refers to when they draw like the peak and trough in the hospital. But yeah, I don't know. I guess it's blood, but I wonder how do they refer that to like.
What's that?
They like when they draw like a peak and trough in the hospital.
Oh.
In the lab.
Uh-huh.
Does it? Or the nurses does it. For blood.
They talk about peaks and troughs there? Wow. Is that studying the pumping of your blood?
Blood, I think. Is that right?
Wow, that's interesting. Now I can see if you're doing a pulse, what you hear, the peak would be when you feel it, and the trough is when it goes down. Is that what they're talking about?
Respiratory is the one. Respiratory therapy is the one.
Okay, yeah, now I can see that too, because when you breathe out and breathe in, breathing out would be a peak, I would think. Breathing in would be a trough. Yeah.
That's interesting.
Yeah. So all these are waves. Believe it or not, light comes in waves. What that is electromagnetic energy, and you don't see the peaks and the troughs there, but they still have them. Okay? So basically, energy is transferred by wave motion. Energy is transferred by wave motion. Okay? Sound energy, light energy, whatever kind of energy. That's why I said the pumping of blood, that's energy that's doing that. Peak, trough, you know. And the breathing, peak, trough, you know, that kind of stuff. A wave is a disturbance that moves through a medium or through space. It can go either way. Okay? My talking, that requires there to be something between us, air, that carries that wave along. Okay? However, the light, especially light coming from the sun, that's going through space. It doesn't require any medium. It just requires an electromagnetic field, which we're going to get to in a later chapter, so we won't worry about that yet. Okay, I was just seeing where these are. This first illustration in your text showing springs in series with a form of elastic medium, it's rather a made-up kind of problem, but you can imagine if you pinged one of those balls, then you're going to see the others start moving, pinging back and forth, you know. That's, the ping is the energy, and the wave is the thing that carries that energy. Okay? Now, that term elastic medium, remember what elasticity was? We did that in the last chapter. Something that returns to its original shape. So pinging it means it's going to move, but then try to get back to the original shape. And then the wave that carries that energy is what goes. Okay, if particle A in the figure that's in the book was to oscillate about the equilibrium position, then all the other particles will start oscillating as well. Now, what a single pulse is. A pulse is a non-repeated disturbance that carries energy through a medium or through space. A single pulse. Now, one of my favorite medium or illustrations of this, I remember this when I was a child. I don't know why I got such a kick out of doing this. But if we had the hose strung out across the yard and we're watering something, and we're through doing it, I like to get the end of the hose and do this to it. And then what happened? That thing goes all the way down there, sort of like a snake or something, you know, just going up and down. It loses height as it goes, but that was a wave. I did one single pulse, and then that pulse traveled down the hose. Now, it lost energy as it went, but it was still fun to see how far it could go, you know. That was a pulse, okay? A disturbance, a non-repeated disturbance that carries energy through a medium or through space. Now, through space, that will require electromagnetic energy. Sound energy, hoses, they won't do anything through space, but okay. Now, if the pulse is repeated periodically, then a series of crests and troughs will travel through the medium, creating what they call a traveling wave, okay? That one pulse travels too, but this one will be continuous travel, okay? Now, going to talk about two different kinds of waves here. The first of these is what they call, the one I was just showing you, is the transverse wave. Trans means against or across, okay? And what I did, my energy went up and down, but the wave went that way, right? So the energy was like this, but the wave was like that. So they were in cross directions, okay? That's a transverse wave, okay? That's one type, okay? Now, before we go off of that, on that transverse wave, the amplitude was the amount, the distance I went up and down. Okay, if I went up and then down, but then came back to here, this is equilibrium. That's up, that's down. Now, if I just went up and down there, it just has, that's the equilibrium. But the amount of displacement from the equilibrium, that is your amplitude. Most of the time you have a wave that goes up and down, so the amplitude is right in the middle. I mean, the baseline, the equilibrium is right in the middle. The amount up or the amount down, that would be the amplitude. Okay? That's the amplitude of a wave. And we're going to see an illustration of it. In fact, let's go and get it up there. Okay? Now, this is talking about transverse waves, of course. This would be a measure of the amplitude. Or that would be a measure of the amplitude. They don't list that on here, but that's what your amplitude is. Okay? The height or distance above the equilibrium line. Okay. If a spring is compressed on the left end and then released, now that's going to be this picture, okay? Then you have what is called the longitudinal wave. This is a transverse wave. You pick something up and the wave goes that way, okay? Water waves are pretty much transverse waves, okay? Now we're going to talk about other characteristics of this wave as well, coming back to the crest and trough a little bit later. So let's go to this one. This is the longitudinal wave. This time, you have the spring up there, and you're compressing the spring and pulling it back. The compression, then you'll see that compression go down the spring. And the rarefaction, which is when you pull it back, that goes down the spring afterwards. Now, here's the difference. Your push was in the same direction as the promulgation of the wave. So that's why it's called longitudinal, in the same direction. Longitude is pretty much along the wave. Okay. And this is an illustration of this. When I'm talking to you, these waves here, sound waves are compressional waves. These are longitudinal waves, also called compression waves. Transverse wave is sometimes called a shear wave because it's going in the opposite direction of the transmission. This is going in the same direction of the transmission. The direction of wave travel this way, the direction of the particles is that way. They're in the same directions. Whereas the transverse wave or the shear wave, the motion was up and down, but the wave travel was in that direction. But the motion that got it started was perpendicular. Okay. Now, let's talk about some of the characteristics of the wave. Here we go. Here's one of them. This is called the wavelength. Now, this is showing for a transverse wave. It would work if it was a longitudinal wave as well. We'll go back to that slide. But it's measured either from crest to crest, from trough to trough, now, the equilibrium, you have to be careful, okay? If it's from the equilibrium position, it must be going in the same direction. So here's that equilibrium again, but it's going in the opposite direction, or a different direction. There it's going in the same direction, so that would be a one wavelength, okay? Or it could be any places, like here to here, as long as it's the same location going in the same direction. That would be one wavelength. The symbol for this, length, is in the Greek alphabet. The letter that's similar to our L is there lambda. That's a lowercase lambda. Huh?
Like Kappa and lambda?
Yeah. Is that a sorority or something? Or yeah.
I don't know.
Yeah, yeah, but they use Greek letters, so that's why they call it the Greek system, But yeah, that would be the lambda. Now, they probably use the capital lambda for that, but it's still the same letter. In the Greek alphabet, they have capital letters and lowercase letters, just like we do. But they look different, okay? Some of them are very different, okay? So that's the wavelength. Now, that's a length, wavelength. Just like amplitude is a length, how far above or below, okay? Now, the time it takes, now this is a traveling wave. Let's go back to one of these slides. Okay, we'll use this on to the other one too. Okay, this only shows one wave, so I can't do a wavelength on that one. Let's do this one. Okay, here is crest to crest. That's your wavelength, trough to trough, that's your wavelength. This is your amplitude up and down. That's also a length. But now if this wave is traveling in that direction, and we could use this one too, that one's traveling in this direction, okay? But the time that, say, this particle, now this particle is just moving up and down. It's not going that way. The energy is moving that way. With this particle, like that hose, I do it like this, and the hose just goes up and down, but the wave travels that way. So the time it takes for this one, as it's traveling, right now it's here, a little bit later it'll be here, 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 and for it to go one wavelength further down the road here, the time it takes for that to happen is called the period of the wave. So the distance from here to here is the wavelength. The time it takes for one wave to go from here to here, exactly one wavelength, is called the period of the wave. Okay? So that's another one. They're not showing it on this one, but they will show it a little bit later. Okay? Now, this is interference. So, they don't really show well here the period, but let me do it. Let me get my pen back. All right. So this is a wavelength. That's a lambda. But the time it takes for it to go from here to here, the time is called the period. Now, they usually use capital T for period, or I sometimes just call it PER for period. That way it's a little easier to tell. Now, period then would be the time it takes for one cycle. This is called a cycle, for it to go from this point here to go down, up, to back to its right. That's one cycle. So the period is in seconds per cycle. Cycle isn't really a unit, but seconds per cycle. It's seconds, right? What if we had the reciprocal of that? 1 over the period. This would be cycles per second. That's called the frequency. So frequency is the reciprocal of the period. Whereas a period is how many seconds it takes to make one cycle, the frequency is how many cycles you get in a given second. How many cycles per second. Now, y'all all deal with these, I bet. Ever turn on a radio? That's in so many kilohertz, okay, or megahertz, or gigahertz, okay? Those are all frequencies. Okay, how many cycles per second? And those are getting some big numbers there. Kilohertz is thousands, megahertz is millions, gigahertz is billions of cycles per second. Okay. Now, we've been using that saying Hertz. That's named after Heinrich Hertz, who's mentioned here in the book, a German physicist from way back, 1857 to 1894. That was in Germany. He lived from a little before the war between the states here till close to the turn of the century. So he didn't live a super long time. What was that? 47 years? 37 years. That's pretty sad. Okay. But the unit for frequency is named after him. He did some of the early work in that. All right. And there's the formula. And they use it exactly the same way. Frequency is 1 over period. They use capital T for period. All right. Now, what if you are trying to get the propagation velocity, the velocity of a wave? I will put V sub W for wave velocity. Well, remember I said what distance that is? That's the lambda divided by the time it took for it to travel, that's the period. There's your velocity of your wave. The lambda divided by time. Wavelength divided by time. But what was 1 over t? Frequency. So another title for it would be lambda f. The wavelength times the frequency, because 1 over t is frequency. 1 over period is frequency. So there's several formulas you can use to go back and forth between that. Those relationships apply to sound, to water waves, to light waves, all other kinds of waves, okay? Just what medium it's going through, and light has a fixed velocity, by the way. All right, let's do example 1. Sorry, I've got the coughing going on. So let's get out of this one and go back to this one. All right, we'll go from current slide. All right, example 1. Find the velocity of a wave. So we're let me get my pen back. Okay. All right, we're looking for the velocity of the wave. That's the unknown. Find the velocity of the wave with a wavelength. What's the symbol for wavelength? Lambda. Looks like a, yeah, a little bit like a backwards H. Okay. I think of it as a gecko who's sort of despondent, okay, or something like that. I don't know. Okay. Velocity of wave whose wavelength is 2.5 meters, okay, and has a frequency, that's usually F, frequency of 44 hertz. Now, what is a hertz? A hertz is a cycle per second. So you can call this 44, and they use the symbol per second. That's okay. It really says it pretty well. You'll also sometimes see it like this, 44 seconds to the minus 1. That also means per second. And sometimes you'll see it, in the old days they used to do this a lot more than they do now, CPS, cycles per second. But cycle isn't really a unit, so they don't use that much anymore. Okay? So, what is the velocity? Anyone remember the formula? Lambda times the frequency. Perfect. So this will be 2.5 meters times 44 per seconds, which is not a bad way to do it. And this would be, multiply those two together, and you get, what, about 110? I'm guessing? 100? Yeah. Is that right? 110? And that would be meters per second, which is a great unit for a velocity, 110 meters per second. That's moving pretty fast, okay? Because the 44 hertz is a pretty high frequency, 110 meters per second. Now, this next thing that we're going to hit here is called superposition of waves. And let's go back to the slide set, and they do a okay job of illustrating this. Okay? All right, here we go. Now, let's say we had these two waves. Here we have a wave that looks like a given amplitude and a fairly high frequency, several wavelengths per second. Okay? Here is another one that's about the same amplitude, but it has a much longer wavelength, which means a much slower, lower frequency, you might say, assuming this is the same time scale. So what you're doing, you're adding these quantities. Well, they both start at 0, so you're going to start at 0 here. But then they're both going up, so this goes up faster than either one of them because they're both on the way up here. And along about here, you see they've reached their max, somewhere pretty close to where they cross here, okay? And then, because this was going down, that was still going up, you start bending a little here. And then when this gets to 0 here, this is exactly your superposition. It's right there. Now they're both going down, and this one's going down, this one's going down, so the whole wavelength goes down until these two get exactly equal to each other. This one's above and this one below. Now your superposition's at 0. Now this one's still going down, this keeps going down, but now this one's coming up, and then when they cross, they happen to both cross 0 here, so the sum is 0. But this trough here is not as high as that peak was there. The crest was there. But then you go through the same thing. This one's going up, but this one's going down, so you don't have as high a peak. And then they come back to where they're equal. That's where that's 0. And when they get close to being both negative, you have this. So now we do have a pattern here. Now what this creates is a pulse. A heavy beat here, light, light, heavy in the opposite direction, heavy, light, light, And that's what gives you a beat. And I bet you've heard that when you've had, say, I don't know if you ever played with a synthesizer. I haven't, but I've heard people do it. And you can create these beats going on. Anyone have a keyboard that has some toys are like this, and you can set it up to different frequency, and you can then hear the beat going on in there. That's exactly what's coming here. Now, what this is called constructive interference, this is called destructive interference, because here these are competing with each other, so they wipe it out and make it go to 0. This has energy here, that has energy there, but they're in opposite directions, so you wind up with 0 there. And then, so this is destructive interference here, constructive interference there. So heavy beat, light, light, heavy, heavy, light, light, heavy, heavy, light, light. So that's what you have. But one's in one direction, one's in the other. So that's what we mean by interference. Okay. Now, have you ever seen when there is an oil slick over water? Have you noticed the colors you get from that? And that's because it's breaking the light down into the various frequencies of light, and that gives you the different colors. Pretty interesting thing is that film of water is thinner or thicker, you see different amounts of refraction in it. So, I bet you, I don't know sonography, so I can't tell you what's going on, but I bet you'll be listening for things like beats or watching for things like this to give you indicators. When I was in the Navy, my first class midshipman cruise, I had been thinking about going submarines. When my mom heard that, she was not very happy, okay? So I wound up not going submarines. But I was on the submarine cruise that summer between my junior and senior years, and they have sonar men on board. And other surface ships have them too, but the submariners really count on these guys. And those guys are so good, they could tell you how many propellers this ship had and how many blades on a propeller. They were that good by studying the beat frequencies and about what speed it was going. They are so incredibly good at that. They also could recognize different ships sometime. If one of them they knew had a chip on one of its propeller blades, and it would give a little whine. And they would say, that sounds like the blah, 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 or I haven't heard that one before. Let's record this and see if we can figure out who that is. So they were really good at it. I'm not sure y'all will have that kind of sophistication in it, but I bet you do get to do some pretty neat stuff. All right. Now, the next topic they have here is what they call the standing waves. Now, I've asked this question several times before, but have any of you been to the McLean Science Center downtown? It's a really fascinating place. There was one place over there, I don't know if it still has an exhibit, that you had a thing that would create waves, and you could spray a mist of water and shine a light on it, and you could see the waves. They really weren't standing there, but that's what they looked like. They were going so fast back and forth, but they would look like a standing wave because they were just at the right frequency that you do it. But they were moving like crazy, but they looked like they were perfectly still. Well, this is what this is. When a transverse pulse wave, we talked about that, reaches the end of a spring that's fastened to a rigid support, the pulse is reflected back along the spring. And that's what they say spring, along the string, I think it is. I thought I read that. Yeah.
Spring.
It does say spring, doesn't it? I thought so. Yeah. Bizarre. I would think string, that looks like what it is. But if you were to do this, and it's traveling this way, and if this is fixed here, when it bounces off that, it's going to go here, go here. When it bounces off here, it inverts and starts going back this way. Okay. Now, if you had a whole bunch of these on top of each other, then after a while, and you got the right frequency, the ones up and the ones down would be right there at the same nodes, is what I call it. Okay. That's what we call a standing wave. You have to have it just the right pitch, you might say. Now, any of you play any stringed instruments? Guitar, ukulele, but you've seen people play banjo, any of those. When they hit those sweet notes, that's when they have their finger on the fret here, and when they pluck this, it sets up a standing wave there, and each one of those is a different note, so they can be playing, and that's how they make harmony and make good things, because those frets are set up just to be the frequencies that the notes that go together really well. Okay? Just like piano chords. Okay? Now, the wave displacement, okay, in one special case, two waves combine so that there's no propagation of energy along the wave. The wave displacements are constant, remains in a fixed location, and that's called the standing wave. And they look like they're just standing there. They really are moving back and forth really fast, but they look to be perfectly still. Okay. Let's see if they have this next slide. Yeah, here's one. Now, and by the way, any of you ever played a horn of any nature? Yeah. You have. Which kind?
Clarinet.
Clarinet. Okay. What you're doing there, you're blowing on this end. This end's open out here, and you got the keys, or what you call these, whatever they're in between. Okay. Second.
I said, I think they just call them keys.
Yeah. Okay. Well, what you're doing is setting up different waves along that, and depending on which one you're doing, and if you get a sour note, it doesn't sound good. But the rest of you wouldn't do that. But yeah, I did all the time. I played piano, and I said, well, and if I ever try to sing, I don't just hit white notes or black notes. I hit the cracks in between. That's where my natural vocal capabilities are. I'm terrible. My wife's okay. Never mind. All right. This is exactly 1/2 of a wavelength, right? So let's say this was your fixed end where you're blowing on the clarinet, and there's the opening at that end. When that's one thing like that, you have 1/2 of a wavelength. This is one wavelength. You go here to here. So that's exactly one wavelength. One peak, one trough, and you go back to the equilibrium position. Exactly one wavelength. This is 1.5 wavelengths. This is 2 wavelengths. Okay? One wave, 2 waves. So the length of the clarinet doesn't change. Okay? But where you put your fingers and that kind of stuff, that does change, and that affects which notes you play. Okay? So this is a string, but the same thing can be held for a clarinet or any other instrument like that. Your piano chords, when you hit the note here, if you've ever seen open the back of a piano and watch, you have a little hammer hitting a certain thing. And the tuner who has come in has tuned those so they're hitting each note perfectly. So then when it hits up a standard wavelength, half wavelength, or whatever, 1.5, whatever. And that's what you're doing when you're playing the piano too. Your guitar, you're moving the thing. You're not changing the tension. Of course, to start with, they tune the guitar by turning the little frets at the top, or whatever you call that at the top, get it in tune, and then every fret that you hit, you're changing the notes. Sharps and flats and next note up. Okay. Now, next picture is pretty interesting. Don't know if you've ever seen something like this before. A pool of water and you have something sending sound up there, and when it's doing this disturbance, then it's sending forth and making patterns like this. The line of the nodes, that's where you have the destructive interference. You can see those sort of here, 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 here. You see those? Can you picture those there? Those are the lines of the nodes where they're crossing each other. You see, here is one issuing, and they look like these are the same frequencies, but they're at a different time. But again, you get a little bit of a beat thing. Here they're constructive interference. There's a destructive interference. Okay? Constructive, destructive. Okay? And that you get this pattern here. You see it. You see the pattern. Okay? You hear the pattern. The line of nodes would be like that instrument at the McWane Science Center, where it looks like they're not moving at all. Yeah. Pretty incredible how that works. So that's interference and diffraction. Okay, so interference we already talked about. Where two troughs cross, the water is lower. The water level is lower than for one alone. Okay, if the trough crosses a crest, then the water level is undisturbed. So that was your wave interference, where the two crests, you have constructive interference, two troughs, constructive interference, where they going exactly opposite each other, then you wipe them both out. Okay. All right. Now, diffraction is the property of a wave that describes its ability to bend around obstacles in its path. And here it's going to be, well, yeah, this is sort of a picture of this. I don't see this exactly in the text, but the picture is, oh yeah, there it is. It just snuck up here. Surprising. Okay. Here we have what we call plane waves coming in, almost straight level waves coming in. These are, say, the peaks, and those are the troughs, or whatever, but coming in. Well, then if you have a blockage here, then the wave that comes here gets to keep going through, and it travels through as if nothing's bothered it, because it didn't. But here it's meeting interference, so it's dragging, the friction is dragging it back, so now you've gone from a plane wave to a curved wave, okay? And your wavefront, that's what you call these things, are now moving in different directions. Here the wavefront was moving all in one direction, okay? The diffraction of a sound wave entering a room through a door, water waves passing through a small opening, like a jetty, is that what you call it? I think so. You'll see the waves do that kind of pattern. Okay. Let's see if they have another picture here. Yeah, this is the one right next to it. This is actually a thing. So you see the water waves coming in almost parallel to each other. Not exactly, pretty close. And then they get here, and this part comes in almost undisturbed, but these start bending, and you have very definitely a wave front pattern going in like this. So this is how waves operate. They talk here about water pool or wave pools. Isn't the one up at Point Mallard or something like that up near Huntsville? Yeah, okay, I've never been there, but my grandmother used to take my wife's mother used to take the grandkids there a lot, you know. They expend a lot of energy and she didn't have to do very much, okay. Actually, there was a place in Munich when we visited friends there where the water from this creek, they built this park over it so it only has one little outlet here. And when it comes in with such force, it's a lot like this. And people are there surfing in Munich, Germany, which is so far from the closest beach, but they can do it because it sets up this type of thing. So anyway, this is playtime, okay. And there's your wave, typical human-made wave pool, okay. You pump the water up here, and then it comes down, and then it comes back just like it does on land, and where it comes back in underneath, that makes the wave crest, and people are body surfing or whatever on top of the wave. Just like this. Okay. Fun summer activity. Not this time of year. Oh, this is one at Typhoon Lagoon in Disney World. I didn't know that. Okay. Now, we're going to move into electromagnetic waves. These are the light waves, gamma, all sorts of electromagnetic waves. Now, before we get there, we probably need to give some definitions. So let's go out of this and go back to this one. Okay, from current slide. And get my pen back. Oh, goodness. At this point in the week, I'm running out of energy so fast. Okay. Yeah, 4. Okay. An electromagnetic wave is a transverse wave. Now, here's something interesting about electromagnetic. Notice the name, electromagnetic wave. Does that sound contradictory? Don't they call it electric wave or magnetic? No, it's a combination of the both. You have electric wave doing like this, while the magnetic wave's doing like this, but they're not quite in phase, so they're at the same frequency, and that's what transmits the energy. It transmits really high-level energy, medium-level energy, low-level energy. Radio waves are electromagnetic waves. Gamma rays are electromagnetic waves. Light waves, light is electromagnetic waves. Electromagnetic wave is a transverse wave resulting from the periodic disturbance of an electromagnetic field, which has an electric component and a magnetic component, each perpendicular to the other, both perpendicular to the direction of travel. It's really an interesting thing. Now get this, all electromagnetic waves travel with the same velocity. That velocity is, they call c. You know what c is? The common name for it? The speed of light. Speed of light. All electromagnetic radiation travels at the speed of light. Okay? Now, I'll give you the SI unit for that. The speed of light is 3.00 times 10 to the 8th. That's a lot of zeros, meters per second. Okay? That would be, 10 to the 6th would be millions. So this is 300 million meters per second. Okay? That would be 300,000 kilometers per second, which would be about 186,000 miles per second. 186,000 miles in a single second. That is, if you can imagine the globe, if you were going around the equator of the globe at the speed of light, you would go, I think it's 2 or 3 times in a single second. All the way around the earth, 2 or 3 times in a single second. That's moving. That's why it seems like light is instantaneous. but it's not. It does have a finite speed, and that's what it is. Now, remember the velocity formula we used before? V is equal to, what was that? Lambda times the frequency, right? Well, guess what? That's constant for electromagnetic radiation, so that constant is C is equal to lambda F. So if you know the wavelength, you know the frequency. If you know the frequency, you know the wavelength, because the speed is constant. 3.0 times 00 times 10 to the 8th meters per second. So frequency and wavelength are inversely proportional to each other. As the frequency goes up, this wavelength decreases. As the wavelength increases, this frequency decreases. Okay, they go in opposite directions, inversely proportional. Okay, we got time for example? Maybe not. All right, sorry about that. Thought we'd have time to do example 1, but we don't. We'll start with example 1 next time, and that's the only example in this section, so we'll have some problems right after that, and then we'll get into sound waves, which for y'all will probably be a little more important than what we've been talking about here. Okay? Now, we did finish chapter 12, so let me give you your test for chapter 12. Got to find what I did with them. I just ran them off when those guys came in. That's one reason it held me up. Still waiting on 2 tests to come in. 2 of your first tests. There's 2 people. Not you. Y'all have turned those in. But I'm talking about the other folks. All right. Here is test 3. We've got 4 of you here. I think that's enough. All right, there is one correction to be made. I've already made it on here, but I just want to point it out to you, make sure you understand what I was doing. Okay. Now, on question 3, and this is exactly printed from the test bank, and when I looked at it, I said, what in the world is that? 50,00. That's no such number. You always have 3 digits after a comma. They only had 2. So that should be 50,000. Whoever typed this really did a lousy job. And then on part B, what if that were 60,000 pounds? So that's the 60,000. So those are the corrections there. Okay? All right. Pretty straightforward, I think, following pretty much what we did. I meant to pass these out as soon as we finish the chapter, but I forgot to. So, good deal. Good class.